view sheet, which if you don't have one, you can get one here. Hoping people will have questions, but if you don't, that's okay. We'll do it again. Let me first
I'll take everyone.
let me first
Can you tell me whole stack?
take that.
Yeah, we'll really appreciate it.
Yeah, that's okay.
Oh, never mind.
I was no,
I saw one.
When I said the midterm, it's on Monday. Are you gonna take it here?
I have my sister's.
Take it here? I think please.
Here in class or in the testing center?
We have an option.
You can take it in the testing center.
Really? Can I take it later even?
You have to talk to them. That's why I'm asking.
I didn't know about this option at all.
Is this your, which one? You're using the accommodation for all of this class or do you use it in somewhere else? Do you use your accommodation only in this class or in somewhere else as well?
No, I have only this class and I have online classes too.
Okay.
So I don't know.
No, normally you can take the test in the testing center. Quiet and silent area.
And how much time we have?
1.5.
Like running over the camera.
Thank you, man.
So, let me start by repeating my apology for mixing up the assignments. I kind of gave the law of sines assignment and the law of cosines assignment in the wrong order. It's kind of, I got confused, but I think the book really has the two in the wrong order, but that's the order they have it. So again, we've done them both now, so I don't think we have a problem anymore. Are there any questions on, any of the last three homeworks that people still have?
Yeah, the last homework, number 27.
Okay, you want to give me the page?
It's a law of cosine.
Law of cosines? Okay, so,
It's the flag.
and which number?
27.
Sorry?
27.
27?
The last one.
The flagpole?
Yeah.
Okay, I think I might have done this before. I feel like the wording of this is poor. It says there's a flagpole outside her school. She wants to know how tall it is, so
I was late.
we have a flagpole. And it casts a shadow 66 feet 5 inches long. That's the shadow here, right? And the angle of elevation is 36 degrees. See, it doesn't really say from where. I mean, the only logical thing is from the end of the shadow.
The shadow could change too. The shadow length could change.
Well, the shadow will change, but so will the angle. You mean as the sun moves?
Yeah.
Yeah, but this is a moment in time.
Okay, so there's a ratio there that's always like the constant. Or something like that. Like the angle changes as the length of the shadow changes.
Certainly.
Okay, so it's always going to be the same.
What's fixed is the height of the flagpole, right? But say, let me just kind of, let's say we look at this at a different time of day, and the shadow will be, here it's, what did we say, 66 feet and 5 inches, and here it might be somewhat shorter, but the angle will be somewhat steeper. So this is just a moment in time. We're not worrying about the fact that it's going to change.
No, I know that, I'm just,
Yeah.
I wasn't thinking about the whole picture, I was thinking just about the length of the shadow changing, but
Yeah.
not the angle. So
I mean, we could say it's like 2:30 in the afternoon, right? And the shadow is this long. That kind of fixes it.
Right, and then the hot elevator, it might be a little longer, a little shorter, a little longer.
But then the angle will change.
Right.
Yeah. So what we have here is, this is of course, should be a right angle where the flagpole meets. And we have to look and see, well, what trig function is going to relate this height, the length of the shadow, and the angle. And the obvious trig function is the tangent. The tangent of 36 degrees should be the sine over the cosine, or h over 66 point. It's not 66.5. It's 66 feet 5 inches, or as I would prefer, 66 times 12 plus 5 inches is what? 66 times 12 plus 5, or 797 inches. So solving this, we rearrange and find h equals what? 66, well, I'm just going to write it as 797 inches times the tangent of 36 degrees. And that'll give us some number of inches, which we might, if we lived in America, we'd probably want to switch back to feet, but if we lived anywhere else, we'd probably want to switch it to centimeters and meters, because it's much easier to deal with. Do you need me to go ahead and calculate? Okay. All right. Are there any other problems? Any other triangle problems?
Maybe 21, of the homework, 9.3.
Okay. 21. Distance to a ship.
What section?
Okay,
9.
this is very apropos, because we're going to look at something in a few minutes. We got to get some scrap paper here. Run out. Called triangulation, and that seems to be what this problem is about. We have a ship over here at sea, and we have an observer A who sees the ship at 40 degrees along from the bank, from the shore, and an observer B who sees it as 46 degrees. The distance between the two observers is 524, and what we really want to know is this distance D. Okay, well, let's just think this out for a second. What do we know right away we can figure out? I mean, using the law of cosines, we can find out this angle. Oh, we don't need the law of cosines. We can just use the fact that the triangle has 180 degrees. So what does that come out to? 86. 180 minus 86 is 94 degrees. Okay. using the law of sines, we can then
Number 21.
find these two sides, right? Well, at that point we're good. Because if we know B or C, right? We know this is a right angle here. We know this is a 40 degree angle, so we can use the sine function, right? We know B over B is the sine of 40 degrees. And then we're good. Again, if you want me to calculate it, I will, but if we're going to find B and C, or C, you could use either of them, using the law of sines, right? We know that sine of 94 degrees over 524 will equal the sine of, say, 46 degrees over B. So that'll enable us to solve for B, and knowing B, you can use this equation to solve for D. You good? Okay. All right. Other questions? Questions on homework? 23 on which section? Oh, the Coast Guard one. Oh. Okay. Triangulation. We're really going to do a lot with triangulation today, you can see. Okay, so there are two stations, on 1 and 2, and they're getting a signal right from our boat. Okay, so now this is terminology which I'm not gonna quiz you on whether you can figure out this terminology, but you know, they give you a little hint here. This is north, south, east, and west, and ship in stresses. Okay, the location of the ship from the first station. Actually, I think I have them backwards here. I think this is 2 and this is 1. Is 34 degrees west of south. So what do they mean by that? Well, this is south, right? So they mean 34 degrees west. Okay, that's one angle. The second station is 41 degrees east of south. So that's this angle here. Well, that might be the confusing part of this, because they're not telling you these angles. You can figure them out. This is, you know, I guess this again is poorly worded, because from their diagram, they clearly want you to think that these two are at the same y coordinate. But it doesn't actually say that, does it? I don't see how you could figure it out. Well, there would be a way. But in any event, it looks like this angle must be, what, 49 degrees? Because this is a right angle. And this angle must be 56 degrees. That tells me my third angle, right? That's 90, 105, 75 degrees. And we know that the distance between the stations is 105 miles. So from that, we can use the law of sines to find this distance, So it turns out that the distance from 1 is 71 miles, and the distance from 2 is 90 miles. So if they're going to send help, they should send it from 1. And then you just have to do a velocity calculation to find out, inverse velocity calculation to find out how quickly they'll get there. I guess it's 71 miles over 175 miles per hour. That's about 24 minutes. That all sound okay? Other homework questions? I have some homework questions I want to go over. All right, let me proceed. What I want to point out is, we've learned now how to solve these triangles. There are two situations that in doing the homework myself, I realized are a little tricky, and I want to kind of clarify so that we're not confused by them. One of them is on page 634, problem number 13.
What section?
So, you might not have been confused by this. You might have just kind of gotten the answer right away, but okay, so we have an angle T and a triangle PAT, where P is 6, A is 7, and T equals 12. So if you just go and attack this without thinking too much, just applying what we know, you might proceed as follows. You might say, well, let's find the angle across from P, right? So using the law of cosines, I would say 6 squared equals 7 squared plus 12 squared plus 2 times 7 times 12 times the cosine of angle P. Okay, that's fine. We solve and find angle P. Minus. Thank you. So we work that out, and I guess I'm just going to work it out. So this is the inverse cosine of 6 squared, 7 squared, minus 12 squared, over minus 2 times 7 times 12. Okay? So that's pretty straightforward. See if I can squeeze it into one quick calculation here. 6 squared minus 7 squared minus 12 squared divided by minus on another parentheses, minus 2 times 7 times 12. Oh,
This is not
I'm in radian mode. All right, that's okay. I can fix that, right? Multiply by 180 and divide by pi. So I get, let's just say
No, this is not the right one.
it's not the right one. I'm not surprised. All right. Let me change my mode here. This is not the confusing part I wanted to look at. Okay, so you're saying, all right, let's just figure out the number here. 6 squared minus 7 squared minus 12 squared is divided by minus 2 times 7 times 12. And I want to find the inverse cosine of,
Professor, I think there is a plus, like 6 plus 7 minus 12.
Why? When you take it to the other side, it's gonna be negative.
Yeah.
Why would you wanna do
I think that's the right number.
it? Yeah.
Okay. So I'm just going to call this, for the sake of
The last answer is
efficiency, 21 degrees. All right, so now I say, all right, I want to find angle T, right? So I go ahead and say the sine of 21 degrees over 6 must equal sine of angle T over 12. All right, so my angle T is the inverse sine of, oh, that's nice, it's just 2 sine of 21 degrees. All right, so we're pretty close here. So inverse sine of 2 sine of 21.
Got
And I get 45 point, we'll say, I'll just say 46 degrees. All right.
Okay.
Now, the problem with this is that's the wrong answer. Why is that the wrong answer? Well, it's the wrong answer because the inverse sine could be 46, or it could be 180 minus 46, 134. So how are we supposed to know that? Well, it turns out you can use a little common sense, right? If you draw the thing, what's it going to look like? This is 12, this is 6. I don't even have to draw it real accurately to realize that this is an obtuse triangle. And that's why it's the larger angle of the two. Now, you'd say, well, all right, that's all well and good. What if it's close and drawing a picture isn't going to help me? Well, in that case, you want to think about the Pythagorean theorem for a second, right? Let's look at the Pythagorean theorem with respect to this, okay? These are obviously the shorter sides. 36 plus 49 is 85, and 12 is 144. So it's obviously not a right triangle. Because it's an obtuse triangle, the square of the longer side, not hypotenuse, but the longer side, is greater. If, on the other hand, I had an acute triangle, let's just take a ridiculously simple example. Let's say this is equilateral triangle. If I look at two of the sides, 36 plus 36, this is now greater than the square of the other side, 36. So we know this is an acute triangle. So this is, one of the trickiest things you're going to run into in solving triangles, where if you just use the law of sines and cosines without thinking about the fact that the inverse sine could have multiple values, you could run into some trouble. Something to keep in mind. All right.
So, Professor, why did you get P angle, not the T directly?
I'm sorry?
Why did you get the P? Because they asked us to find the T angle, and you start with the P.
Well, this is not an example of how to do something. This is an example of how not to do something. Sure, if you use the law of cosines on 12, you're going to get the right answer right off the bat. Okay?
So the exam, should we do like the new way or just the normal way?
Well, what I'm alerting you to is the possibility that when you use the law of sines, you know, you have to be careful,
Okay.
right? That's the lesson here, not do it my way. I mean, you know, do it the smart way, right? Okay, there's one other issue that we talked about a little, but I want to clarify it. It has to do with the situation you get into with SSA, side-side angle. And I'm just going to draw a diagram here. So we know side A, we know side B, and we know this angle, I guess we should call that angle B. So without looking too closely here at this diagram, because it's set up a certain way, there are a number of possibilities you could run into here, right? Well, in this particular case, I think you can see that if B is greater than A, you're only going to get one solution. Right? There's no other way to arrange this triangle, you know, given that it looks like this, as long as B is greater than A. However, if B is less than A, well, actually, let's cover all the possibilities here. What if A and B are equal? Well, this is a really easy problem then, right? Because whatever angle B is, angle A has to be the same, right? It's an isosceles triangle. From there, you can easily figure out the third angle. And there's obviously only one solution here. Where it gets interesting is if, I'm going to draw, take a new sheet, what happens if A is greater than B? Well, we have the possibility here that there are actually two solutions. But there's worse. You could have this situation. You could have a right triangle. These are all cases where A is greater than B. And then there's a third, even more ugly possibility, which is that there's no solution at all. Right? B could just be too short. So how can we differentiate between these? Well, one thing that's really good to look at is the value. I'm going to use theta because I like theta here. Is if you look at the value A sine theta. Now, A sine theta is the height of this point here over the side. It's the length that B would have to be for this to be a right triangle. So if B is equal to this, A sine theta, then you have a right triangle. If A sine theta is greater than B, then you have this situation, which is no solution. And if you have A sine theta less than B, then you're going to have this situation where you have two solutions. I guess I should write that in A sine theta less than B. Now, keep in mind, this is conditional on A being greater than B. Right? I mean, if A sine theta is less than B, A could be less than B, and then we go back to that single solution. So this is a little complicated. You might want to, spend a little time thinking this through. Because if you get a question on the midterm where it says, an SSA question, you want to be prepared to say, okay, there's got to be this one solution, or two, or no solutions. Okay, are there any questions about this? This is, I think, the trickiest part of solving triangles. Okay, we're going to have a little intellectual interlude here. We'll get away from hard stuff. I have a, yes?
Is it possible to go over a midterm review first before we
No. It's not. We have some other material I'm going to cover today too. So, I found this video on this disc, and it's actually, of all the little snippets, it's the most interesting one I've run into. I learned a lot that I didn't know. Where are you? I did something. I had no idea how they found out how tall was. I had no idea how surveyors survey an entire landmass. And I think it's only about 7 minutes, but I found this pretty exciting, so hopefully you will. You getting any sound yet? Okay. You're not getting any sound. What has changed? Yeah.
Can you exit the full screen?
Yeah.
The voice is kind of mute. If you go up to the top bottom, yeah, the voice. You close to the Wi-Fi, yeah.
Huh. Yeah, that's, it does that when I plug in the HDMI cable. But it's not listening to my computer. It's not playing on my speaker.
Can you go settings sound?
This has to do with this sound system. And I've never really played with this. But apparently, since I was last here, someone has. So, all right, I'm just going to give it a couple more seconds, and I'm going to give up.
Can you go settings audio on your
It's
Mac?
not the computer that's in charge of this. It's yes. All right. I don't want to waste your time. I'll figure out how to make this work, and I'll show this some other time. It's just really interesting. If you remember, one of the problems talked about something called a theodolite, and they explain what that is. So, all right, I'm sorry. Technical difficulties. All right. Okay, Moving back to where we were at the end of the last class period, we're going to talk today a little bit about polar coordinates. Polar coordinates are like Cartesian coordinates. On a plane you have two values, but instead of an x and y coordinate, you have an r and a theta coordinate. And r and theta tell you relative to the origin, which is sometimes called the pole, they tell you the angle and the radius to get to any particular point. One has to be a little careful with polar coordinates because they are not unique. For example, the point radius 1, angle 0 is the same point as radius 1, angle 2 pi. Another example is radius 0. If you have 2 points with radius 0, their angles can be anything, but they're still the same point. They're still the pole. And lastly, you have this complication that if you take a point, say 1, 0, and negative 1, pi, these turn out to be the same point also. Because if you go 0 angle out 1, or if you go 180 degrees and then negative 1, you end up in the same place. So that's something to be a little careful about with polar coordinates. They're not unique. Okay, so I want to talk a little bit about something that we're going to work with a little in this class today, which is what is a polar coordinate equation. And just like in Cartesian coordinates, we can have an equation with x and y, you can have an equation with r and theta. Usually, we have an equation of the form r equals some function of theta. In a very simple example would be r equals, say, 3. So let's take a look at what that would look like here. I'm going to have to change it. Let's say r equals 4. R equals 1.5. Does everyone see what this is? It's just what you might expect. The radius is a constant with respect to theta, so it's just a circle. Okay, that's a very simple polar equation. Yeah.
So is it always going to be like, is the midpoint always going to be 0, 0, or like on the x and y? The midpoint always going to be 0, 0.
The origin is always radius 0,
Okay.
and it can have any angle. Okay. A lot of very interesting curves you can create using a polar equation. A real basic one is some number, let's say 1, plus another number, 0.5 times theta. Okay. This is called an Archimedean spiral. It should actually continue, but the grapher is just going to go from 0 to 2 pi. We can do the same thing on our calculator. I want to show you how. So there are some things you want to note here. First of all, probably want to be in grading mode. And then if you go below here where it says radians, you'll see there's a few different options. Func is what we've been using. That's for an x and y. But 2 over, you get POL for polar. So we're going to put it in polar mode. And now when we hit the y equal button, you're going to see the equations now are r equals, r1 equals, r2 equals, and so forth. So let's try that same equation, 1 plus 0.5. Now when you hit this xt theta n, you jump to the wrong place. You get a theta. And we should take a good look at our window here. All right, let's start with theta going from 0 to pi, and let's see what this looks like.
Wow.
Okay, we probably want to zoom out, don't we? Okay, but that didn't go very far, so let's improve this a little. Let's say 3 pi. Try it again. All right. One more time here. Now, you notice a feature of this Archimedean spiral is that if you draw a radius across here, the points it intersects are equidistant.
So
Which, if you look at the equation, kind of makes sense, right? The first time around, I'm 1 plus 0.5 theta. And the second time around, I'm going to be take a look at this. 1 plus 0.5, 2 theta. I didn't say that right. First time I'm around, I'm 1 plus 0.5 theta. But the next time around, I add 0.5 times 2 theta. And then 4 theta, and then 6 theta. So it's a constant
So the next time will be
difference.
1 plus theta, right?
Hmm?
The next time will be 1 plus theta?
All right, let's just take a look. What if I'm looking at 45 degrees, right? So 1 plus 0.5 times 45 degrees is pi over 4. The next time around, it's 1 plus 0.5 times pi over 4 plus 2 pi. And then 1 plus 0.5 times pi over 4 plus 4 pi. So as we go between these, we get this 0.5 times 2 pi, or pi difference between them. Okay, this is called an Archimedean spiral. There's another kind of spiral that
Hey, Professor.
I want to mention, which is you could have some number, let's say 0.5 raised to theta. This is a little different. I think it'd probably be better to show it on here. Now we're going to have to play around with the window. Decided to change all these for me. Let's start with 2 pi. And minus 2 plus 2 minus 32 plus 32. So you can get a. Well, this is actually part of the game here, is figuring out how to do this right. I think I'm going in the wrong direction. I think I'm going in the wrong direction. Yeah. All right. So I think maybe minus 1. 1 will get me closer. Minus 1. Yeah, this is exponential. We're going to. Ah, there we go. Okay, so if I zoom out, and then I increase this to 4 pi. Okay.
I think you should zoom in.
Zoom in.
Or standard, zoom standard.
Oh, you know, I know what's wrong.
Oh.
I'm this is less than 1.
Oh.
If I say 1.5 raised to theta, I'll get what I was thinking about. Okay. There we go. Now I can zoom out and you can see a little bit more. All right, so this is an exponential spiral. You can see that the distance gets further and further away much quicker. Okay, let's just take a look at a few other examples of what you can do here. All right, what would one think cosine r equals cosine theta would be? I think that'd be a somewhat interesting curve, but actually it's just a circle. It's not a circle on the pole, but it's just a circle. Similarly, sine, let's give this a little size here. R equals sine theta is also a circle, this time sitting on top of the x-axis instead of sitting to the right of the y-axis. All right, what does multiplying the theta by a factor do? Oh. So suddenly we have a 4-leaf clover. How about if we divide? How about if we divide theta by 2? Okay. Has anyone ever seen this curve before? It's called a heartioid. It's heart-shaped, sort of. Kind of turn your head
Or
sideways.
something else shape. Or something else shape.
Or something, oh, okay, all right. Let's try. Okay, well, anyway, there are a lot of fun little shapes you can do with, fun little graphs you can do with this. We're gonna do some of them. I want to point out
I don't.
a few little interesting things here. Back. Oh, there we go. So this is an exponential curve, and it actually appears in nature quite often. See if I can do this quickly. Right. If you're not familiar, this is called a nautilus shell, but this is often used as an example. There are other examples. Some flowers, kind of their petals grow this way as an exponential curve. This kind of curve was actually investigated by a fellow named Bernoulli. Anyone heard of Bernoulli before? Bernoulli's principle, that's right. That's one of the Bernoullis. Right? You know, some of the, well, okay. This is Jacobus Bernoulli. This is his gravestone. And this is just very typical of what happens when you order your gravestone after you die. He came up with the exponential spiral, but on his grave they put an Archimedean spiral. What can he do about it, right? Right. So, who is this guy, Jacob Bernoulli? He came from a family of well-known mathematicians and scientists. The Bernoulli principle we talked about comes from a Daniel Bernoulli. The Bernoulli we just spoke of, Jacob, was his uncle. Jacob had two brothers, Johann and Nicholas, who were also famous mathematicians. Daniel was Johann's son.
Is it Jewish family?
I don't think so. I don't think so. I could be wrong. Daniel had a brother, Johann too, who was also a famous mathematician. Johann's son, Johann the second's son, Johann the third, was a famous astronomer, geographer, and mathematician. And Johann also had a son, Jacob II, who was a famous mathematician. I just, you know, there's the family tree. You know, it just shows you, you know, how little your own family has done, right? Like, you've got half a dozen mathematicians and scientists. I've never heard an explanation other than, you know, they were well educated and an inquisitive bunch. Okay, that was a little diversion.
Is there a finger?
I don't know.
There's one eyeball there.
Oh, let's see.
Finger on the left. Nicholas?
Hieronymus,
No,
Nicholas,
no,
Hieronymus,
On the left side.
Jacob, Nicholas. Oh, painter, yes. I've never seen any of his artwork. Yeah, creative family. You can all aspire. Okay, all right. We're going to do a little work with, you know, let me back up a step. the curriculum throws in these polar coordinates right here, and we're gonna look at them today, and then we're not gonna look at them again. So you might ask, why are they here? As far as I can tell, the main reason is because when you get into calculus, especially, well, I don't know about the calculus 1, 1B, but certainly in the 2B, we look at polar coordinates and we do the things we do with calculus with them. We measure lengths and areas. So they insist you not go into that class having not been exposed. We do need to know how to do a few things with polar coordinates. We need to know how to convert to them and away from them. So if I have some point here, it's at r theta, I have to know how to get my x and y coordinates from this. And this is just a straightforward application of our trigonometry. So if you look, we have a right triangle here and our angle theta. And so we can immediately, from our r theta coordinates, get x and y using the formula x equals r cosine theta and y equals r sine theta. Converting back is a little trickier, but finding r is not hard at all. We just use the Pythagorean theorem. We know r squared equals x squared plus y squared. So r is just the square root of x squared plus y squared. Finding theta is a little bit tricky, right? The formula we use is theta is the inverse tangent of y over x. So let's look at this. Why is that? Well, you can see right away that clearly the tangent of theta is y over x. So y is just saying that theta is the inverse tangent, not okay all by itself. Well, if you think about it, what if the point was at the exact opposite location? Right? So we now have negative x and negative y. Well, the tangent of this angle, which is theta plus 180, is the same. The tangent of this angle is the same as the tangent of this angle. So it's not adequate enough to just use this formula. You also have to think about which quadrant you're looking at. Well, how do you do that? Well, if you look at your x and your y coordinates, if they're both negative, right, you're in the third quadrant. This is pretty straightforward, application of what we've done before. Similarly, if your tangent is negative, you could have a value out here in the first quadrant, or you could that same value. You would get the same value for the inverse tangent if it's over here in the fourth quadrant. So now you have to look at, okay, if one of these is positive and one is negative, you have to look at which is which, right? If we have the cosine, or the x positive, we have the x negative and the y positive, then it's going to be here in the second quadrant, first quadrant. And if it's reversed, we're now in the fourth quadrant. So again, converting from Cartesian coordinates to polar, you have to be a little careful to get the angle right. Okay, if you like charts, here's a little chart that will kind of explain explain this all. X and Y both greater than 0. Quadrant 1, X less than 0, Y greater than 0, 2. Both of them negative 3, and X greater than 0, Y less than 0, 4. If you happen to be a computer programmer, you might like to know that most languages, C language, will come with their math. Their math package will have a function they'll call tan2. Tan is just the tangent function. I'm sorry, arctan2, where you give both X and Y, and it figures out which quadrant and gives you the right value of the theta. Okay. There is a little more I want to talk about polar coordinates, but I'm going to give you guys a break now, and we'll be back in, say, maybe 10 minutes.
On December 12th,
Okay.
like after the final. You wanna go? $39 for one of my
Yeah.
tours for
No,
No?
no.
Is it
Unambiguously simple,
simple?
really. Whatever you think simple would be, it's either simpler than that or the same as that.
Show,
Isn't it extra
show
credit?
us.
Less than or equal to.
Will you show us? You just
I
show.
probably already have. Okay, I was driving here today, and I was thinking about how awkward this stuff is. We just kind of show you some clover leaves and how to graph it on your calculator. And I thought, I don't feel very good about that. And then I was thinking, well, what could you use this for? And I have a long drive, so I have a lot of time to think about it. So I came up with a kind of a real simple thing that I think it's worth thinking about for a minute, because we have everything we need to do this, pretty much. What I was thinking about is, has anyone here not flown in an airplane? Oh, good. Has anyone ever gotten worried when they're flying in an airplane? How do they know where they are, or how do they know they're not going to run into each other? So if you watch enough, movies, you know that there are these guys. They're called air traffic controllers, and they sit in a dark room in front of a kind of a greenish screen, and there's kind of a sweep that goes around because on the top of the building there's a radar thing going around, and you see little bleeps, right? Little airplane bleeps, right? And well, what kind of coordinates are they getting these in? They're obviously polar coordinates. They get an angle depending upon where the sweep is, and the radar tells them how far away the item is, right? So I was thinking to myself, well, these guys, they just look at the screen and they kind of know how to do this. But what if you wanted to write some computer software that was going to automatically warn them when two planes get too close together?
There is software like that.
Yeah, I'm sure there is.
Inside the airplane, it's a long time ago they had invented.
But I'm not talking about in the airplane, I'm talking about the air traffic controller.
Oh, okay.
So, so here's the idea. I thought it was neat that the answer was just so obvious, at least part of the answer. So if I have one airplane, who's, we call him R1, theta 1, right? And I have another airplane, he's at R2, theta 2. First thing I want to know is, how close are they together, right? There's got to be some minimum distance, right? So given these, how can I find the distance between them? Well, it turns out we already know how to do this, right? Because here we have R1 side of the triangle, R2 side of the triangle, and the angle here, that's just going to be the distance between these two angles, right? Let's call that delta theta. Well, what we want to know is this distance, and how are we going to find that? Law of cosines, yeah, right? I mean, let's call this x, right? So we know x squared is r1 squared plus, plus r2 squared minus 2r1 r2 cosine of delta theta. Well, okay, that's the first part. So immediately, if we're too close, we set off an alarm. My notes here. Right. But the next thing we might want to do is we might want to predict, right, that two things might get too close, right? And I was thinking about that, and I was thinking, well, we could just convert this to Cartesian coordinates, but let's say we didn't want to. We want to stick with our coordinates. So we want to be able to watch one of these guys. I don't know if you know, they, along with being visible on the radar, they also transmit a call sign. I think if you remember the tragedy that happened, I don't know, a year ago or so, this airplane was Malaysia.
Yeah, Malaysia Airlines.
Yeah, well, they turned off the call sign, so, it wasn't, we couldn't see them anymore. So that's why they think there was something going on, it wasn't just an accident. I mean, I don't want to talk about gruesome things, but, the 9/11 pilots did the same thing. They immediately turned off this signal. They could still see them on radar, but they didn't know who they were. All right, so we can watch one of these guys, and we can see where he's going. We can kind of plot 2 points. So we want to be able to plot a straight line, right? Which, normally we do that. We say y equals mx plus b. And if you have 2 points, that's enough to figure out what n and b are. But how would you do that with polar coordinates? Well, if you recall the translation, we have y equals r, what was it? R sine theta, and x equals r cosine theta. So if I substitute these in, I get r sine theta equals m times r cosine theta plus b. Well, if I want to plot that, I probably have to combine the r's, right? So put both of these on the same side, mr cosine theta equals b, take out the r. And now I can actually solve this, right? R equals b over sine theta minus m cosine theta. So that should be the equation of a straight line. We should check that out, right? So here we go, we'll just make up some simple numbers. R equals 1 divided by sine x minus, well, we could just, n could be 1, right, cosine x. And I'm gonna have to fix my window here, I think. Well, that didn't work. Oh, because I didn't put in parentheses where I should have. I'm just going to start over. 1 divided by sine x minus cosine x. There you go. Got a straight line. So again, I could use this equation. By the way, this doesn't work under one circumstance. Can anyone think of a circumstance this wouldn't work?
With 0.
Well, yeah. In other words, if sine theta is equal to n cosine theta, you're dividing by 0. But, or if b is 0, right? But if b is 0, this is just a line going through the origin. So, you have to use that as a special case. But anyway, so now we can figure out, the equation of the trajectories of each of these, and we could say, all right, if they're going to intersect within such and such amount of time, we could also signal. But when I was doing this, I said, well, that worked really well. But I wonder if that would work for other, work for a line. Would that work for anything else? So the first thing I thought of was, well, what about y equals x squared? What's that the equation of? It's a parabola, right? Right. So plugging in here, we have r sine theta equals r squared cosine theta. And now let's solve for the r's again. Divide by cosine and divide by r. So I get sine theta over cosine theta equals r. Oh, that's just a tangent. That sounds too easy. Let's give that a try. What happens when I graph the tangents? I have some kind of window problem again. Hold on. Oh, wait. Cosine squared. Oh, that's a little different, isn't it?
Tangent divided by cosine?
Tangent divided by cosine. Thank you. Ah, isn't that nice? So, you can do stuff with, polar coordinates other than just full reliefs and other interesting curves. I'm going to suggest if you haven't taken one of these sheets, you could take it. There's just a few little problems you might want to try converting coordinates. And then on the back, if you want some fun, you can program these into your calculator and you can see some pretty curves. I'm gonna leave polar coordinates there. What I'd like to do for the rest of the class is either field questions or go over the review sheet, and we can do that informally if you wish. I'll let people ask questions, and if people don't ask questions, then you'll just hear me talking. So let's go. start you off. You should know what a function is. You should know what the vertical line test is and what it means. Know what the domain and range of a function. And you should know about inverse functions and periodic functions. Yes?
So when you're doing these problems for changing the curve equation order to step on your calculator, you're going to be doing degree mode with the polar.
You can use degree mode or radian mode, but you have to keep track of which mode you're in, right? In other words, if you figure out an angle is too high and you're in degree mode, there's something wrong.
Yeah, and you're going to use that polar function too, right? That polar?
Well, the polar function is for graphing.
Okay, so you just use that function. Does it not really matter?
Let me kind of show you where, let's do something simple here. Let's just say a little bit more than this. Let's say 1 plus cosine of x. Right? So if I graph this, you see I get a little circle. Or actually a cartoid here. So if I look at my window, I'm going from 0 to 2 pi. Now, if I were to switch that accidentally to radian to degrees, it's still going to go 0 to 2 pi degrees. So you're not going to see much here. I don't know if you can see there's a little bit of function over there. So if you're in degree mode, you might have to say 360 degrees. The calculator's not going to. It's working its heart out. The reason it's having trouble is because I changed this to 360, but the step is still really small. I changed the step to something normal. There it goes. It's probably still a little too small. Okay, I guess I should have. Nope, it's going the rest of the way. Okay? If you can do that, you'll be fine. All right. Going back to the beginning of class, you should know what radian measure is. You should know the relationship of radian angle to the radius and the arc length of a circle. You need to know how to convert. I think everyone's pretty good at that. Do not underestimate the importance of knowing those two important triangles, 30, 60, 90, and 45, 45. Knowing the ratios, right? 1/2 square root of 3 over 2, and 1, I guess,
3?
I think,
Oh,
I think it's been decided everybody in here likes to rationalize the denominator, even though I don't care. I'm sorry. Question?
No question.
Okay. You want to know these like the way you know your 2's times tables. Standard position of a triangle on a unit circle. Okay, it's like in the first quadrant. Directed angles, coterminal angles. most people have gotten this down, but not everyone. If you have any question about what I mean by an exact answer, please let me know. Please voice it now, because, yes.
Yes, I have a problem. I mean, can you repeat again what's the exact answer?
Well, let me give you an example. Let's say I have a circle, and I tell you the radius is 2. And I say, what is the circumference? Right? So you say, well, the radius is 2, the diameter is 4, so for pi, that's about 12 point, I don't know, whatever it is. This is not an exact answer. You cannot write 4 pi. You can't. You don't have enough time. There's an infinite number of digits. So this is the exact answer I'm looking for. Right? Now, I don't think it will come up. But if I said, what's the, I have to draw myself in here. If I said, what's the cosine of 30 degrees? Exactly. Well, if you plug into your calculator is going to tell you 0.866, right? That's not an exact answer, right? There's something else behind it, and you can figure it out at square root of 3 over 2. Now, if I should be so rude as to say, well, what's the sine of 23 degrees exactly? You're stuck. All you can do is you can say it's the sine of 23 degrees, because there's no way for you to write it exactly other than that. At least not at this point in the class. So, similarly, if I said, what's, I don't know, 83 divided by 15, and I want the exact answer, right? Well, again, if you go 83 divided by 15, so you're going to get 5.533. Now, if I don't really like decimals, but you could get away with this if you do this. Right? Because that tells me it repeats forever. But you're much better off either, leaving it the way it is. Well, actually, no, there's no factor of 3 in there. No, that's it. That's an exact answer. Yes?
So you said the cosine of 30 degrees is equal to negative square root of 3 over 2?
Yeah.
Isn't there like a way you can do that by hand? You can figure that out that way.
Figure.
You can just do it like, couldn't you just write it out?
I always like my little diagram, right? There's my 30-degree angle, my 30, 60, 90 triangle that I know through and through. And I know this is the square root of 3 over 2, and this is a half. So the cosine, right, is the adjacent over hypotenuse, so it's square root of 3 over 2. I mean, figuring out the triangle is a different issue, right? I think I talked about that at the beginning of the class. If you're caught on a desert island and you need to know this answer and you forgot, just take an equilateral triangle. The angles are 60, right? 60, 60. Okay, this is going to bisect that angle, so it's going to be 30. These sides are 1. This bisects here, so it's a half. And you can find the height using Pythagorean theorem. Exactly. So, All right, any other questions about that? I don't really care if you know how to round. I mean, you should, not for this class, but in general. How to convert revolutions per minute to radians per minute, or degrees per minute.
Professor,
That's just a conversion.
for polar equation, are we gonna get a polar equation during the term? The one we just
You might,
learned?
but if you're listening carefully, I said it would be
Small one.
simple.
Yeah, but like,
And then he said, well, maybe what you mean by simple is not what I mean by simple. And my response is no.
so it has to
This
come.
has to be really simple. Yeah,
Okay.
really simple. Okay. Angular velocity. Radians per second is radians. Radians per time is radians over time, right? Pythagorean theorem, of course, you all know at this point. Definitions of the sine and cosine, including, if I have some angle in some other quadrant, right, you should be able to figure out whether the sine and the cosine are positive or negative, right? Is this working well, or should we go about this in some other way?
Can we go over number 9, like in an example?
Okay, sure. So, Tina,
Yes.
that problem you just mentioned from the quiz said truck was, doesn't look like a truck, looks like a turtle, traveling 20 meters per second. And I want to know, and the tires, let's change it, we'll make it simple. The tires are, they're 1 meter in radius, that's a big tire,
It was
right?
0.
So how fast are they traveling in radians per second and in revolutions per second? So radians per second is easy, right? This is 1 meter, the radius is 1 meter, so we just divide 20 meters per second by 1 meter, and we get 20 radians per second. Okay, so how many radians are there in a revolution? 2 pi, right. So to convert 20 radians per second, to revolutions per second, I just divide by 2 pi. So that's 10 over pi RPM. Now, if I ask for an exact, that's how you leave it. If I don't, you have a choice. You can leave it like this or put it in your calculator and divide. So that's revolutions per minute. Degrees per minute. How many degrees are there in a revolution? 360. So what would I do with this?
Convert it into degrees.
Multiply it by,
Pi.
I'm going to convert a revolution to a degrees. How would I do that?
180 over pi.
No, be careful, this is revolutions. It's like one time around. How many degrees are there in one revolution? 360. So I just multiply by 360.
What's gonna happen to the pi?
It's going to stay there.
Oh.
It's going to be
Ah,
360 over pi. That's degrees per
yeah, to
degrees
convert,
per second.
to convert
Per
from
minute,
radians.
per minute.
What
Yeah.
about second?
Hmm?
But you have radian per second.
Oh. Right. So I want to, so this is,
This is.
oh, I
this-
left out the, oh, I left out something here. I converted the radians, but I didn't convert the seconds.
Yes.
So let's go back, fix that. So it's 10 pi radians per minute. So how do I convert radians per minute to radians per second?
No, you have radians per second. You need,
Yeah, you have
Oh.
yeah.
Thank you.
you need,
How do I convert radians per second to radians per minute?
Divide by 60.
I'm sorry, not radians. Revolutions. This converted it to revolutions. So now I want per minute, right?
Divide by 60.
So they're less,
Divide by 60.
right? So divide by 60. So now I have 1 over 6 pi revolutions per minute. And if I wanted degrees per minute, there's more of those, so I multiply by 360. Okay. Other questions on this? Of course, you should all know the definitions of tangent, cotangent, secant, cosecant in terms of sine and cosine. Number 15 is kind of all encompassing over the last few days. How do you solve, oh, I'm sorry, it says right triangle problems. That's simple. That's not all problems. 16 says general triangle problems using Pythagorean theorem, log sines and log cosines. So we've been doing that this last few days. I guess this kind of skips around. You know the plus or minus sign, negative or positive in each quadrant. I said secant of, say, 5 pi over 6. Is that positive or negative? How do we figure that out?
Be 1 over the cosine of 5 pi over 6.
It's 1 over the cosine. And how will we figure out where that is? Okay. Well, this is pi, right? So 5 pi over 6 is just this angle here where this is pi over 6. And the cosine is the x-coordinate, right?
So it's negative.
So that's this direction, so it's got to be negative. I think I'm not sure if I gave you this chart, but at some point, you know, you want to do this as an exercise. So we start with pi over 3, and pi over 4. No, start with pi over 6. Pi over 4, pi over 3. Next, pi over 2, and 2 pi over 3. Just, you know, all the multiples of pi over 6 and pi over 2. So you get over here to, I guess the last one would be 2 pi minus 1/6, which would be 11 pi over 6, right? So every one of these is either, you know, like a 45 degree angle, or it's a 30, 60, 90. So every one of these, you should be able to figure out what the sine and the cosine is exactly. And therefore, you could figure out what all the other functions, the tangent, the cosecant, the secant. Everybody comfortable with that idea? You can do that? Okay. What else? This is a problem apparently I got it backwards on the homework. I was corrected
The solution.
how I did this, but this is actually
Can I ask?
I didn't understand that.
it's a nice little problem. How would I solve this? Well, let's be a little careful. Let's say from 0 to 2 pi. So the first thing we'd want to do is we find the inverse sine of both sides, right? So 2 theta is inverse sine of 0.47. This is a problem that could show up as an exact problem if this was a number like square root of 3 over 2. All right, so the number your calculator is going to give is going to be one valued sine, right? But it also could be 180 minus. So those are two values that could equal to 2 theta. So theta could be either of these over 2. But that wouldn't be the whole answer. Actually, why don't I give you some numbers here? So inverse sine 0.47. This is about 28 degrees. And then 180 minus 28 is 152 degrees. So the question is there any other thetas you could plug in here that would be between 0 and 2 pi?
360 now?
Plus and minus 360.
Because you also already,
Well,
360 minus
you
the
see,
sign.
if you add 360 to these, they're outside of this, right?
Yeah, no, I'm saying for like,
Minus.
you can do 360 minus this inverse sine of 0.47. Trying to find it.
I don't think that's going to be an answer, though.
Yeah, okay, I was just asking if
Yeah.
that was a possibility.
Well, I think one way to look at this is a periodic function, right? So every 360, this is going to be the same value, right? But it's 2 theta, right? So actually, if I add 180, right, when I multiply it by 2, it's going to be 360, so it's going to come around. So I can also add 180 to each of these. And 2083s. So when you see like something like sine or cosine or one of the other functions, n times it, where n is greater than 1, there's the possibility you can squeeze more solutions into here.
Is that how you find all the possible values within that?
Right.
By
right.
adding 180, or you wouldn't be wanting to?
Well, in this case, I can add 180 because 2 times 180 is 360. So if I add 360 to what's in here, it's got to be the same, right? That's its period.
Okay. And if it's greater than 2, like if it's like 3 or 5, or
Okay,
you
so
use the
this
same
were,
method, or would you have to kind of approach it?
let's forget all this other stuff for a second. So if this were 3, then what could I add to the initial values I got?
60.
How about 120? Right? And how about 240? Right? If I was so cruel as to say 5 theta, well, the pattern seems to be, right? So that's what, 72. So I could add 72, 144, 116, and 288. I'm not inherently a cool person, so I wouldn't worry too much about
Okay. Thank you.
that. Right. If I ask you, what is the domain of, I don't know, let's just say cosecant of x. What is the domain and range of cosecant of x?
Domain is 5.
5?
5.
5. Okay. Happens. Well, this is 1 over what?
Sine. I'm sorry, sine is 2 pi. So
What's the domain of sine of x?
2 pi.
Not the period. The domain.
Sorry, 2.
Well, isn't it 180?
Okay. Try again. What's the domain?
5 or 2 plus.
You guys are overthinking this.
All real
What
numbers.
numbers can I plug into the sine?
All real.
From
All
0
real
to
numbers. Thank you. All real numbers. That's the domain of the sine. Right.
It's the pattern with the.
But the cosecant, you can't plug in all those values, right? Anything except where sine of x is 0, right? So where is the sine of x 0? So it's all reals minus, you could say x such that, this is the nice mathematical way to say it. But if I wanted to know what this is, what values of the sine of x 0? You know, 0, right? Pi, 2 pi, oh, I see, it's n pi, right, where n is an integer. that's the domain. What's the range of the cosecants?
-1 and 1.
Okay, that's the range of the sign.
Except for 0.
Hmm?
Except for 0. Except for no.
No, zeros,
No,
yeah. Zero's in the range of the sign. What's the range of the cosecant? It might help to remember kind of this picture.
Yes.
So if this is the sine, right? There's the cosecant, and it has an asymptote there, right? And it's also down here. So it starts at 1 and goes up, but also -1 and goes down. That's its range.
So, from negative infinity to -1.
Yeah.
Yeah. Negative infinity to -1, or 1 to infinity. Or you could write it out, you know, like the notation.
What's different from the parentheses when you do a circular parentheses?
Ah, very good question. So, if I have a line, right, and I have a point on the line, let's say 1, and I have another point on the line 2, but I'm going to draw it as a little empty circle, right? So, and then I'm interested in this line segment here, right? So here I'm including 1, right? But I'm not including 2, right? This is what we call an open interval, or this is, right, it's half open, half closed, but it's closed on this side and open on this side. So I write it 1, 0, meaning, 2, excuse me, meaning I don't include 2, but everything up to 2. And here I am including 1. Now, there's something I'm not going to explain, I'm just going to state as a fact, right? For some reason, if I want to say all positive numbers, right, that goes from 0 isn't positive. All numbers greater than or equal to 0, right? So it's 0 to infinity. This is always an open interval when we're using infinity. We can't really include some number infinity because it's not really a number, it's just this idea. Okay. Yes,
Are we gonna be allowed to know like a page numbers?
absolutely. For all quizzes and all tests, you can, you want to write in, you know how those people, they write on a piece of rice?
Yes.
Probably copy all your notes, you know, you can read it. Yeah, yes.
How big can that piece of paper
Don't bring it up.
8.5 by 11, please.
What happens if it's 8 3/4?
To be fair, pardon?
What happens if it's 8 3/4 by 11?
8 3/4, I won't notice. I won't look that carefully. But if it's 16 by 11, I will notice.
Or a massive poster board?
Or, you know, sometimes they have, people give me homework and it's got like this, like hairy stuff on it, right, because they ripped it out. I don't care. I'm not gonna look that close.
My first English lesson. Thank you. I asked.
All right, I'll hang out here for a while if you still have personal questions, but do prepare reasonably, do not panic. Just